Greetings everyone. Welcome back to Calc 2. It's time to get more specific with these infinite series topics. So now that we've defined an infinite series and shown the way that we can look at how we're actually summing an infinite series, it's time to start talking about all of the particular types and all of the different tests and all of the different approaches that we have to our basic infinite series. Those are going to be the foundation that we will then build the last half of this unit when we start talking about how these things relate to functions. Okay, so we're basically through all of these different types of series is we're getting the intro into this topic, right? We're building the foundation here. So the first type we want to talk about is the telescoping series. When you hear the word telescoping, I'm hoping you're thinking back when you were a kid and you had that little plastic telescope, or maybe you're thinking of a pirate, right? With the eyeglass telescope, the kind that collapse, right? It's one cylinder inside of another, and you can just collapse them all together. And that's exactly the reason why they're named this way. This is a series of numbers that when you list out a partial sum, a lot of the middle meat of that partial sum adds out to zero. It zeroes out, and you're left with two or three or one, two, or three, just a few terms at the front, and then a term or two at the end, depending on how much of this thing wipes out. Okay, so I have a finite example for you here. And then I want to expand into two infinite examples. And then in the next scene, we'll get a couple of more bigger infinite examples. So the telescoping series is such that you'll see a relationship. It'll usually be two very similar objects. And of course, that's so that things can zero out. One of them will be positive and one of them will be negative. And that's also to help with the wiping and canceling of things, right? So if I write out the sum of this thing right here, I'm starting at 1. Notice I'm going to have square root of 3 minus square root of 1. Then n is 2. I'll have square root of 4 minus square root of 2. Then n is 3. So I'll have square root of 5 minus square root of 3. And then n is 4. I'll have square root of 6 minus square root of 4. And that's the whole series for this one. It's a finite series, right? It's just 1 to 4 there. But notice we get a lot of matching terms in the middle, but positive and negative. Okay, so I've got the square root of 3 here and the minus square root of 3. And then I've got the square root of 4 and the minus square root of 4. And as this thing, progresses on and on, you'll probably also see if I had more terms, the square root of 5 and the square root of 6 would probably have a counterpart as well. So I'm actually left with the square root of 5, the square root of 6, the negative square root of 1, and the negative square root of 2. So then I've actually got the telescoping series just collapsed down to a couple of the beginning terms and a couple of the ending terms. Now imagine this same process, but on a much larger scale for an infinite series. Remember, we break an infinite series into a sequence of partial sums. So when it comes to telescoping series, what I'm going to do is write out a generic partial sum large enough to notice all of the telescoping patterns that occur. So then what's going to happen is I'll take a series like this and I'll go ahead and do the telescoping cancellations, reductions, whatever way you want to look at it, zero outs. And then I'll go ahead and apply the fact that we're wanting the limit of a generic partial sum, a sub k. Remember, that was the pattern that we talked about in the last lecture. You have like a1, a2, a3 are the partial sums. Sum the first 2, sum the first 3, sum the first 4. A sub k is going to be sum the first k elements. and then I let k go to infinity, and that's the limit of that sequence. And if it exists, then the series converges, right? Okay, so that's basically the idea here, except I'm not going to bother listing out all of the first few pieces of the sequence. When it comes to telescoping, I'm just going to skip to the generic partial sum, and I'm going to see how much I can collapse. Once I've collapsed it, I'll have generic terms at the end that I can take limits of and see if this thing actually does converge. Okay, so let's start with this guy right here. I'm going to write out some generic sums here, right? I'm going to start with n equals 0. When n equals 0, I'll call this a sub k. When n equals 0, I've got ln of 10 minus ln of 5. Plus, when n equals 1, I'll have ln of 15 minus ln of 10. Notice, there's that pair up right there, right? A negative and a positive ln of 10. Plus, when n is 2, I'll have ln of 20 minus ln of 15. Right? So then this one and this one wipe out. I'm hoping that you're seeing the pattern here. The first of a certain term and the last of the next one are going to have that same similar pattern. So you can already guess what the next one's going to be. I'm going to have ln of 25 minus ln of 20, right? Okay, now let's get generic here, because remember, this is a sub k. I've already done 0, 1, 2, and 3. Okay, so just this part would be a sub 3. Let's go generic to a sub k here. Okay, so then I'll have the ln of 5k. I'm running out of space here. Plus plus ln of 5k plus 10 minus ln of 5k plus 5. Like that. So this is up to the kth term. Okay? So now what we're going to do is we're going to follow the pattern here. We're going to start collapsing. So if I pick a term, the first of this one and the last of the next one. The first of this one, the last of the next one. The first of this one, the last of the next one. So naturally, what's going to happen? I've actually added everything in between here. I just didn't list it all out. The ln 25 is going to wipe out with the next one. And then so on and so on and so on until I get to the end. And technically, this is the quote-unquote last one because it's k, and I'm doing a sub k. So what's going to happen is the term right before this one is going to have his first one cancel out. Okay? This one will already be gone from the one before him. This one, though, is going to wipe out with this one. Okay? So now what am I left with? I can actually say that a sub k is equal to negative ln of 5 plus the ln of 5k plus 10. And that's going to be any of the partial sums. It will actually get up to this point. Now, if I want to discover the series total, I'm simply going to take the limit of the partial sums as k goes to infinity. That would be negative ln 5 plus ln 5k plus 10. So then this limit, I hope you're noticing, is going to be negative ln 5 plus ln of infinity, which is also infinity, which is therefore going to make this thing unbounded infinite. Okay? So what are we saying? We're saying that the limit as k goes to infinity of the partial sums, the limit of the sequence of partial sums, is unbounded. What does this tell me? That this series is divergent. Okay? Now I know what you might be thinking. Hey, it's divergent. Couldn't we have just used that nth term rule that we talked about in the last video? You could try, but if you take the limit of this sequence right here and you do your algebra on the logarithms, you'll notice that you get the limit as n goes to infinity, you'll have the ln of 1, which is 0. Okay? So this is one of those series right here where the sequence has a limit of 0, and yet the actual series itself diverges. And it's simply because ln is something by itself on this side that's just unbounded. Okay? It does diverge slowly, as logarithms typically do, but it does diverge. Okay, switch gears. Here's a series that you already know converges because we talked about it 2 different ways in the last lecture, right? Now we're actually going to use this method to show without doubt, algebraically step by step, that this thing does actually converge. And the lovely thing about telescoping series is we can actually see what they converge to, because I'll have some sort of remnants once I collapse the telescoping partial sum. So then I'll get some sort of answer. Okay? But it's not in the correct structure, right? I need something that has 2 similar objects and a subtraction. You already know how to take a single fraction and turn it into 2 separate fractions. We did that in the last unit under partial fractions. So that's actually what we're going to do right here for a moment. I'm going to separate out a little section here. And we're going to perform partial fraction decomposition on this fraction. So I've already got the denominator factored out. This is going to be equal to a over n plus b over n plus 2. After I do my multiplications of that common denominator, I'm going to have 1 is equal to a times n plus 2 plus b times n. So then from here, I'll do my little plugins. When n is 0, okay, I have that 1 equals 2a, or in other words, 1/2 is a. Next, if I let n equal -2, I'll have that 1 is equal to -2 times b, because this will 0 out, which tells me that -1/2 is equal to b. And lo and behold, I can then actually decompose these like so. I have 1 over n times n plus 2 is actually equal to 1/2 over n plus -1/2 over n plus 2. And if you want to write it a different way, where it's like 1/2 times 1 over n and -1/2, that's fine. That's actually going to help us out in a minute. This is probably the decomposition that would be more useful to you. So, now I'm going to bring that decomposition back up here to my actual series. I'm going to decompose the series n equals 1 to infinity of 1/2 times 1 over n minus 1/2 times 1 over n plus 2. And this is going to allow me to rewrite the series like this. 1/2 is something I can factor out. And it's a multiplied constant, so I can even pull it out front of the series sigma itself. It's multiplied by the whole thing. And then I've got 1 over n minus 1 over n plus 2. And that's exactly the structure that we were desiring. Two very similar objects that are being subtracted. So that right there is a big red flag for, hey, this might be a telescoping series. Okay, so let's write out a generic partial sum to see what happens. The generic partial sum, let's say that I let this series equal something like b. I'll use capital B this time since we've been using a lot. So b sub k, the partial sum of the infinite series b up to a value of k, is going to be equal to 1/2 times. Now that's the 1/2 out here. So I'm just going to leave it as a big bracket and sort of just pull the 1/2 out of the way. Okay, now when n is 1, then I've got 1 minus 1/3. Plus, when n is 2, I've got 1/2 minus 1/4. Plus, when n is 3, 1 over 3 minus 1 over 5. When n is 4, okay, so I've gotten up to b sub 4 there. And now I want to add the generic one. Plus dot 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 plus 1 over k minus 1 over k plus 2. Like so. Okay? Let's go ahead and do all of the zeros that we have currently. So I've got the negative 1/3 along with the 1/3 here. I've got the negative 1/4 with the 1/4 here. And then we have to start looking at the pattern. Whenever I have something in a term, I look at the beginning of 2 terms down. So that means whatever was added right here, the very next term, the 1/5 would have paired up with it. So that's going to end up canceling as well. And then the next term after that, which is still in there also, it's in that little skip that I did, the negative 1/6 is going to pair 2 terms after that. So that's going to zero out as well. Keep going down the pattern, okay? Keep going down the pattern, and you need to realize that what we're going to get is that this, the front runner right here, right? The 1 over k is going to be paired up with something 2 terms back. Okay, so 2 terms back, this guy is gone. All right, but then I don't have something 2 terms behind this one. Okay, I don't actually have that going on. It would have to be further on down the line. Well, let's see what I'm left with. B sub k is equal to the 1/2, right? The 1/2 times, I have 1 plus 1/2, and then I've got the minus 1 over k plus 2. Okay? So now do the limit. The limit as k goes to infinity of b sub k is equal to the limit as k goes to infinity of 1/2 times, I'll go ahead and add the 1 and the 1/2 here, that's 3 halves, minus 1 over k plus 2. But then as I take this limit as k goes to infinity, notice the only thing that's affected is this right here. And what's going to happen is the denominator will grow infinite. The limit of this piece goes to 0. So this one does actually converge. The limit shows that this is going to converge to 1/2 times 3/2, which is 3/4. Converges. So we answered the big question, does this series converge? Yes. And bonus, telescoping series, we can actually say, what does this converge to? In this case, that series converges to a value of 3/4, which we already saw in the previous lecture, right? We knew that it was going to converge to 0.75. But here we actually see a lot of the reason why it would do that. Because this is actually a telescoping series if written the proper way. And you have the sizes just contributing at the very front mostly. At the very back end, you can see the pieces go to 0, which is what allows this thing to have the ability to converge. Okay? Let's go look at a couple of more examples of telescoping series. So let's get 2 more examples of these telescoping series, just so that you can have some variety in your note-taking and in your observations here. So I've got d equals the sum where n goes from 1 to infinity, and it's of 7/4n squared minus 9. Of course, this doesn't look like a telescoping series yet because I don't have the 2 objects that are similar in structure and subtracted. So of course, I'm going to approach this like we did in the last one. I'm going to use partial fractions to decompose this and see if it does work out. Now, just because you decompose it doesn't mean it will work out. In fact, I'm going to go ahead and spoil you a little bit on this one. It does work out, but say if the 4 and 9 were reversed, it wouldn't work out. Okay? Even though if you could decompose it, it's not guaranteed to actually be a telescoping series. It will be adding and subtracting fractions, sure, but it may not be the exact fractions that need to wipe out to some zeros that collapse the thing. Okay? So not every one of these fraction things is going to be telescoping, but these few examples that I'm throwing at you are. So let's decompose this. I'm going to start by factoring that denominator. I'll have 7 over 2n minus 3 and 2n plus 3. So then, of course, I'll have a over 2n minus 3 plus b over 2n plus 3, which after I multiply my denominators, I'll have 7 is equal to a times 2n plus 3 and b times 2n minus 3. I will use the substitutions where n is equal to negative 3/2. That will cancel out, zero out this one, and leave me with negative 6 times b. So 7 equals negative 6b. Therefore, negative 7 over 6 is b. And then, of course, I'll also use n is positive 3/2, which will add out the other one over here to 0 and leave me with 6a there. So 7 equals 6a. So 7 over 6 is a. And therefore, I can then decompose this into the infinite series of 2 fractions that have a subtraction. So then d will be equal to, I'm going to factor the 7/6 out of both of these. It's going to be 7/6 over one of them and negative 7/6 over the other one. So it'll be 7 over 6 times the summation, n equals 1 to infinity of, and it'll be 1 over 2n minus 3 minus 1 over 2n plus 3, like so. Again, all I did was I factored this 7 over 6 out of both of these fractions. and then the negative that went with the b is still there as my subtraction. Hence why the 2n plus 3 is the one being subtracted. Okay, so now it looks like a telescoping structure. Let's set up the generic term, d sub k this time, the generic partial sum. D sub k is going to be equal to, okay, I'm going to have my 7 over 6 times the whole thing. And then I'm going to start with n equals 1. That's going to give me 1 over 2 minus 3. So 1 over negative 1 is negative 1. Minus, n is 1, so this will be 1/5. Plus, I'm going to plug in 2 now. So that'll be 1 over 1 is 1. And minus 1 over 7. Because it'll be 4 plus 3 there. Plus, next I will have n equals 3. So I'll have 1 over 3 minus 1 over 9. Plus, I'll plug in 4 now. Right? So that's going to give me 1 over 5 minus 1 over 11. Let me go one more. 2, 3, 4. Yeah, when n equals 5, I'll have 1/7 minus 1/13. And then, of course, I'll put in my generic plus ... The kth term is going to be 1 over 2k minus 3 minus 1 over 2k plus 3. Right? It's going to look just like that. 1 over 2k minus 3 minus 1 over 2k plus 3. Okay, so let's look for the pattern. I see a negative 1/5, and then several terms down, I see a positive 1/5. Okay? 1, 2, 3 groupings down. Okay, so 3 quote-unquote terms, 3 partial sums down, 3 groups down. And those are going to add out to 0, of course. Okay, next, I'm also seeing the negative 1 over 7. And again, 3 groups down. So those are going to 0 out as well. So what do you think is going to happen with the negative 1 over 9? The negative 1 over 9 is also going to find something 3 groups down here. So he's going to go away. The negative 1 over 11 is also going to do 3 groups down. The negative 1 over 13 is going to do the same thing. So on and so on. All the way down until I get to the last grouping. And in that last grouping, the 1 over 2k minus 3, the front guy, is going to have something 3 groups before him, okay, adding out to 0 with him. You'll notice that's the way the pattern works. If I'm looking at my current term, the second piece looks at 3 terms down. But if I'm looking backwards, it's the front that went 3 groups back, which is why the 1/3 doesn't have anything, right? Because he's in the front, and there's not something 3 groups ahead of him over here. All right? So that's all of the collapsing that's going to happen. By coincidence, I have a negative 1 plus 1. That's not actually part of the telescoping pattern of this one. It's just a happy coincidence that 2 of the first terms happen to 0 out also. So negative 1 and 1 is 0. I still have the 1/3 though. So d sub k is going to be equal to 1/3 and then minus 1 over 2k plus 3. Like so. Everything else is collapsed all the way up to the negative 1 over 2k plus 3. So then let's do our limit. The limit as k goes to infinity of d sub k is going to be equal to 1/3 minus the limit as k goes to infinity of 1 over 2k plus 3. And hopefully you notice that this is a limit that goes to 0 because the denominator will be infinitely large. And therefore I'm left with a big boo-boo that I hope you caught me on. This is supposed to be times 7 over 6. So I'll just trail it in the back end here. Times 7 over 6. So this is now going to be equal to 1/3 times 7/6, which is 7/18. And therefore this series converges. It actually converges to 7/18. Okay, one more example. This one I don't even need to use partial fractions. I simply notice that I can split this denominator between each of these two, and only one of them is going to algebraically reduce. So I end up with something that looks like this, 0 to infinity, e over e to the n plus 1 minus 1 over e to the n plus 1. I'll just put a parentheses like that. However, this is technically e to the 1, right? So right here I can actually reduce that algebraically, whether you want to look at it as subtracting exponents, or if you want to look at it as I factor out an e or whatever. I'll use the subtracting exponents. Think of it like this. That's e to the 1 minus n plus 1. And what that's going to give me is e to the negative n. Okay, that's what this fraction is going to simplify to. Okay, so then I have that a is equal to the sum n equals 0 to infinity of e to the negative n. That's just 1 over e to the n minus 1 over e to the n plus 1. All right. Well, this looks like a telescoping, doesn't it? Two things that are similar in structure that are being subtracted, and they're only off by a count of one term. Should work out very nicely. Let's do the partial sum a sub k. When n is 0, I get 1 because it's 1 over 1 minus 1 over e, because that will be e to the 1. Okay, next, when n is 1, I'll have 1 over e minus 1 over e squared, because I'll just do 1 plus 1, of course, for the exponent there. Plus, when e is 2, I'll have 1 over e squared, and then 2 plus 1, I'll have minus 1 over e to the third. And I hope you're already seeing the pattern. I'm going to go ahead and write the generic kth term, 1 over e to the k minus 1 over e to the k plus 1. And the pattern is immediate. The ending of one group with the beginning of the next group every time, right, collapses, because you have a minus and a plus of the same thing over and over again. So that you can see this would be with the next one, and then the one right before this would also take out this one. So these are all gone, strictly leaving me with the 1 minus 1 over e to the k plus 1. Right? So then let's skip to the chase here. The limit as k goes to infinity of a sub k is the limit of this as k goes to infinity. And of course, this has a very large denominator as k goes to infinity, which is going to allow that piece to go to 0. You'll notice that that limit then goes to 1. which is actually what my sum will equal to. And so this one converges. Doesn't seem like something with all those irrational e's in it should be able to sum up to something as nice as 1, does it? And yet, in this case, it does. So, telescoping series is all about just finding that pattern, right? And then making sure that the last term of your partial sum does actually have a limit that will allow it to converge, okay? That's going to be the tell as to whether or not the telescoping will converge, is that what that last term is able to do. And make sure that you're checking for that, not just looking at the beginning of the pattern, okay? And again, let me remind you, just because you can break it down doesn't mean that it will always give you the terms that will add out to 0. So break it down and try it out, and if it doesn't work, then you simply have to move on to a different method among the list of things that we'll be doing over the next several lectures. Okay? Next, we need to talk about geometric series. This is another special series that comes up quite often and has a nice, elegant solution to it. A geometric series is formed from a geometric sequence, right? We talked about geometric sequences a couple of lectures ago when we were talking about sequences. So it's just like that. If I have a geometric sequence, in other words, something that is formed by multiplying a constant rate over and over again, or another way of looking at it is there's a constant ratio between any two given terms. Okay, that's a geometric sequence. If you start to sum up those terms, then you get a geometric series. Okay, so here's a couple of examples right here. The A in the geometric sequence is always the first term. And then R represents the value that I'm multiplying to get from one to the next. And this one may not look like a geometric sequence, just the way it's written, or in this case a series because of the additions. But all you need to do is divide. Divide 6.02 by 7. Divide the 6.02 by 7. And notice that I'm getting 0.86. So right here I'm noticing 6.02 divided by 7 is 0.86. Next, I'm going to divide the 5.1772 by 6.02, right? This term by that term. And you'll notice that I still get the 0.86 exactly. And the same thing's going to be true no matter how far down you go. If you pick a term and divide it by the term before it, right? If I divide this way, okay? Or, if you will, if I multiply the other way, right? If I multiply this way, then I'm going to get times 0.86. Okay? So it's the constant rate. It's a ratio between any two given consecutive terms. And that's why we're using R for it right here. The fact that I'm getting the same thing every time I divide tells me that this is a geometric sequence being summed to form a geometric series. So therefore, the 0.86 is my R. And then as I said before, the first term here is the A. So my A is going to be 7. Therefore, I can actually set this up as a sequence S is equal to, let me make a little more space here. I'm going to move it over here. S is going to be equal to the sum n equals 0 to infinity of 7 times 0.86 to the n power. So this will be the series representation of this particular series here, right? The sigma representation for the whole thing. Okay, let's do this one now. I've got 1/2, 5/8, 25 over 32, 125 over 128. So I'm going to do the same thing that we did in the previous one. I'm going to divide. If I divide 5/8 by 1/2, you know, invert, multiply. That's going to give me 5 over 4. Right? 5/4. Anywhere else, if I divide it out, if I say do 625 over 512 divided by 125 over 128, right? Reciprocal, multiply. I'm just dividing a term and the two consecutive terms here. You'll notice yet again I get 5/4. Therefore, I'm getting 5/4 everywhere. I know I only did 2 of them, but notice if I did 25 over 32 divided by 5/8, right? That's a multiplication there of 5/4 to get from that term to that term, right? Times 5/4 there, times 5/4 here, times 5/4 here. So 5/4 is my R. It's constantly being multiplied to get from one term to the next. And my beginning term is the 1/2. So for this guy right here, S equals the sum, n equals 0 to infinity, 1/2 times 5/4 to the n. And that's how we're going to represent these in sigma notation as geometric series, right? This is the kind of setup you're looking for, where I have some number to the n power. Now, of course, that number can literally be anything, and the whole idea behind the geometric series is going to be mostly controlled by that R, okay? I'm going to go through this little process over here to show you how we can prove things are convergent or divergent, but the good news is you don't have to do this process every time for this. I'm going to show you how we can just read a geometric series and basically just calculate what it converges to if it does, or know right away if it diverges. So imagine I have some geometric series, S equals the sum, n equals 0 to infinity of a times r to the n. Just imagine that's our geometric series, okay? So then remember, the way we talk about a series converging is by getting a partial sum and then eventually taking the limit of that, right? Because that's going to be my sequence of the partial sums. So I'm going to set up a partial sum here, S sub k, for this geometric series. That's going to be a plus ar squared plus ar cubed. Each consecutive term is just continually multiplying another r, so you just get one more exponent on the r, all the way up until I reach the k value, right, of that partial sum. So a times r to the k. So here's a neat little trick that I do. I multiply both sides of this by 1 minus r, and I factored the a out. Do you notice every term has an a? I factor it out. And then I multiply both sides by the 1 minus r. To multiply by 1 minus r over here, I first just take everything here and multiply it by 1. So that's what this is. You see, times 1 just gives me itself. Then I take everything here and multiply it by negative r. All that's going to do is increase all the exponents by 1. And then, of course, 1 times negative r is negative r. So then r becomes r squared is r cubed is r fourth, r to the k is r to the k plus 1. But those are all negative. So it's kind of like the telescoping series there. This is about to collapse. R squared, r cubed, see how they all just add out to 0. And only thing I'm left with is 1 minus r to the k plus 1. And of course the a is still multiplied out there. Now I divide this 1 minus r over here, and I have a different representation for s sub k. So in other words, my partial sum can be represented in this nice encapsulated little calculation. So now what I want to do is the limit as k goes to infinity of that partial sum and see what happens. But before we do that, pay attention to this one little part right here. This is basically an exponential because it's some number r to the variable k power, because k is our variable here. Remember, with exponentials, if you take a limit of an exponential number to a variable power, right, because k is my variable, I'm either going to get something that goes off to 0, or I'm going to get something that is unbounded. That's the way exponentials work, right? I've got two different versions of exponential. Exponential can either do this, right, or it can do this, where the asymptote lets it go to 0, right? So I'll get the unbounded kind if it's what we call an increasing exponential. An increasing exponential is one where this thing right here is greater than 1. I need to put another little case in here, actually. Right? Okay. So then, right here, if r is greater than 1, then this limit is going to become infinite, right? This is going to become unbounded here. And that's going to happen here. If I try to take this limit as k goes to infinity, then this piece right here is just going to explode. And I'm going to get an infinite value for the limit. In other words, it diverges. Okay? Next, if I have the case where it's less than 1. Notice I'm using an absolute value on the r too. That's because r can be negative, and it doesn't actually matter. It's really the size of r's value that determines whether or not this thing is going to be decreasing towards 0 or unbounded towards something else. Okay? If the absolute value of r is greater than 1, so it could be 5/4 or it could be negative 5/4. That number's bigger than 1 when you do the absolute value. It's going to go to infinity when you try to sum this up. Okay? Now, if the size of r is less than 1, you're going to get the effect where this piece goes to 0. If this piece goes to 0, all I'm left with is a times 1 divided by 1 minus r. And therefore, that's just some number that this limit will converge to. Okay? So if my value of r happens to be less than 1 in size, positive or negative, but the size of it is less than 1, then that geometric series is going to converge. Okay? So that's really what I'm looking for here. And yeah, there is a special case that I didn't put in the limit here, where it's equal to 1. Just real quick on the side, if r is 1, then basically I have a sum of an infinite number of a values. So I'll just be adding a forever, which is going to diverge. Okay, so I've added in the case right here. If r also equals 1, it's going to diverge to infinity, just by obvious looking common sense here. Okay, if r is 1, it's an easy proof to show that it's just going to diverge because I'm adding an infinite number of some number. It doesn't even matter what a is, as long as a is not 0, but you're not going to have a as 0 because then that would make everything 0. Okay, so if r is 1, you can see that it's just going to go off to infinity. So that case got included right here. And then of course, if it's greater than 1, I have the case where this piece is blowing up in size, in which case it's going to diverge also. So whenever I approach a geometric series, I'm really looking at that r. Okay? So I have two different examples right here real quick. We can determine whether or not they converge or diverge. This top one right here, I'm going to look at my r. 0.86 is less than 1 in size. Therefore, I can say this one does converge. And wait, on top of that, we can also calculate what it converges to. I can say that this is equal to 7 over 1 minus 0.86. That's what I'm using right here. Don't forget, A is whatever your first term is, okay? If you haven't like made the series itself from the sequence and you haven't actually laid eyes on what the first term is, don't automatically assume that the number multiplied is, because that's going to depend on where this counter is, okay? Notice I started my counter at 0 anytime I create it from the sequence here. And that's because when n is 0, the number in front here can be a. But always double check. Sometimes they'll start you at 1, in which case you got to plug in and multiply to find out what your first term was, okay? Whatever the first term of the series is, right? Plug in that first number and double check, okay? Make sure that you have the first term of the series in your numerator over 1 minus whatever r is. So that's going to be 7 divided by 0.14, which, well, that's a cool coincidence, isn't it? I've got 700 over 14 in that case, and can start to reduce that. That would be 100 over 2, so that's 50. And of course, I'm going to double check myself here. Always want to do that. Yep. Cool. So interestingly enough, if I were to add up all of these terms, right? If I add up an infinite number of the terms in this geometric series, it eventually stops adding and converges to the number 50. However, on this guy down here, I'm noticing r is 5/4, which is larger in size than 1. Okay? So because r is bigger than 1, the absolute value of r is bigger than 1, therefore this diverges. It's nice to be able to just look at a series and say, hey, I know that one diverges, just by noticing one little aspect of the series. It's still important to be able to write it out as the series formation, but then also you're going to want to be able to show that it diverges. So in any kind of proof or anything like that, you just write, this is a geometric series with r equals 5/4, and therefore since absolute value of r is greater than 1, the series diverges by geometric series. Okay? Let's get a couple more examples on this one. Now let's finish up this lecture with some examples of geometric series. Of course, we know that they're geometric once we see them in this format, because I can see that it's some r number to an n variable power. And of course, these would be constructed the same way I did the two in the last scene. Okay, so once you have something that you know is a geometric series, right, and you can recognize that by looking at it, then we just inspect the r. Here, my r is 3/5, right? So r is 3/5, and therefore the absolute value of r is less than 1. So we know that this converges. And a lot of times, remember what I've said in the past, a lot of times the question on a series is, hey, does this converge or diverge? We actually get a bonus on geometric series that if it does converge, we can calculate what it converges to. So then this series, I can actually say the series itself is equal to a over 1 minus r. Now be careful. I can already see the 1 minus r, right? 1 minus 3/5. But what is my a value? Remember, a represents the first term in the series. So here, let me show you what I mean. I'm going to erase this to make some space for just a second. my series is going to be where n equals 1 is the first term. So the first term is going to be negative 4 times 3/5 to the 1 power plus negative 4 times 3/5 to the 2 power plus. Okay, so my a is going to be this first term right here. This is my a value. Negative 4 times 3/5 to the 1. So that's going to be negative 12/5. Okay, I'll make this easier on myself by multiplying everything by 5. This is going to give me negative 12 over 5 minus 3. Negative 12 over 2, which is going to be negative 6. This converges to a negative number simply because my negative came from this little factor I had in the front. All right? So this does converge, and it converges to negative 6. Next, I can see that my r here is negative 7/8. And the absolute value of that, right, the absolute value of negative 7/8 is less than 1. This is absolutely true, right? So I can say that this does converge. What does it converge to? Well, let's find out. Let's list out the first couple of terms here. I have negative 7/8 to the 0 plus negative 7/8 to the 1 plus negative 7/8 to the 2, so on and so on. Negative 7/8 to the 0 is just 1, and this is my a. So my a is actually equal to the value of 1, because anything to the 0 is 1. So 1 over 1 minus my r is negative 7/8. Be extra careful. The negative comes with the r in this case because it's part of the thing being raised to the power n. It's perfectly okay to have a negative r. In this case, that's going to make this an addition. So I'll multiply everything by 8, and that will give me 8 over 8 plus 7, which is 8/15. And therefore, this converges to that. Next, right here I can see that my r is the number being raised to the n. My r is 3/2, which is greater than 1. Since my r is greater than 1, I can say that this diverges by geometric series. So that's it. That's all you can say for this one. On this bottom guy here, you've seen this guy before. The sum of negative 1 to the n. We've already proven that this one diverges. But now I'm going to make it even easier on us. It's a geometric series because I have some number raised to a variable power. And you can see that r is equal to negative 1. The absolute value of r is 1, which is equal to 1. It's not less than 1, okay? So the absolute value of r is not less than 1. By this fact right here, it diverges by geometric series. Okay, some of our properties of summations you need to remember, and that is whenever I have multiple things that are added or subtracted, maybe sometimes I want to sum them separately. I know with telescoping series it was very tempting to keep them together so that I can try to get the thing to collapse. But if you notice that you have something that could be geometric, geometric's even easier than telescoping, even if I have 2 of them. So what I'm going to do is I'm going to rewrite this series like this. I'm going to say that it's the sum n equals 0 to infinity of 3 over 2 to the n minus the sum n equals 0 to infinity of 4 over 5 to the n. Notice the 3 here and the 4 here do not have the n power on them. So I'm actually just going to bring those out front and use it kind of like the a part of the term there, right? And then I can actually use the fact that 1 to the n is 1. So look, this is what I'm going to do here. The 3 over 2 to the n, for example, I'm going to rewrite it as 3 times 1 over 2 to the n. But 1 is the same thing as 1 to the n, because 1 to any power is still 1. That allows me to rewrite this as 3 times 1/2 to the n power. And I'm going to do that for both of those guys. So then what I've got is the summation n equals 0 to infinity of 3 times 1/2 to the n minus the summation n equals 0 to infinity of 4 times 1 over 5 to the n. So I've got two geometric series there. And I can see right here the geometric series has a rate of 1/2, r is 1/2, which is less than 1. So this one converges. And here r is 1/5, which is also less than 1. So that one also converges. I will then calculate what they both converge to, and then I can subtract them. Okay, so then this is going to be equal to, what's the first term here? 3 times 1/2 to the 0. 1/2 to the 0 is 1. Okay, so I've just got 3 over 1 minus 1/2 for that calculation. Minus, right, now I'm going to do this one. When n is 0, 1/5 to the 0 is just 1. So I have 4 times 1 is my first term. 4 is my a. Over 1 minus 1/5. Okay, so I can then reduce this to, if I multiply by 2, I'll have 6 over 2 minus 1 minus, if I multiply by 5 here, I'll have 20 over 5 minus 1. So this is 6 over 1, which is 6. And this is 20 over 4, which is 5. So the whole thing converges to 1. So that's what this is going to converge to if I were to plug in and start doing terms of this and adding them all up. This series right here is going to converge to a value of 1. Next, the sum of 7 times cosine to the n of 3. Now don't forget, in trigonometry we use this little shorthand where an exponent goes in between a trig function and its argument. But what that really means is that I have this value to the n. So let's rewrite this to reflect that. I have the sum where n equals 0 to infinity of 7 times the cosine of 3 raised to the n. That's what that shorthand stands for. Well, that looks like geometric series to me because I've got some number times some value raised to the n power. It doesn't really matter. Any number can be in that spot for the r, but if I want to know if it converges or diverges, I need to know if this value right here is larger or less than 1 in size. Well, lucky for us, we remember from trigonometry that cosine of any value, it's one of your properties of cosine, is less than or equal to 1 in size. The only part we need to worry about is the equal to part. Okay, so just remember some of your cosine facts. Cosine of 0 is 1. Cosine of pi is -1. And this is neither of those. It's just cosine of 3, and it's not degrees, so it's radians, right? Cosine of 3 is going to be something negative because it's in the second quadrant, right? It's not quite 3.14, so it's really close to 180 degrees, but it's not quite, okay? But regardless, cosine of 3 is some value in between -1 and 1, and it's not equal to -1 or 1 because it's not pi or 0 in the argument. Therefore, cosine of 3 is an r that's less in size than 1, right? I can say this is for a fact. The absolute value of cosine of 3 is less in size than 1. Therefore, this converges. Well, what does it converge to? That's an interesting question. Equals, my first term here is going to be 7 times cosine 3 to the 0. Cosine 3 to the 0 is just 1 times 7. So I have 7 over 1 minus my r is cosine of 3. Okay? Now in some places, this would be a completely fine, perfectly fine way to leave this if you wanted to leave it in an exact form. Let's also get an approximation here. I can do 7 divided by, make sure my thing's in radians, 1 minus cosine of 3. And I get 3.5176. Is an approximation of what this converges to. Okay, so yes, this one definitely converges because that cosine value is less in size than 1. So you just need to pay attention to what's inside of that r value, right? In this case, the cosine of any number would have been in between 1 and -1, unless it was cosine of 0 or cosine of pi or cosine of 2 pi, one of those things. Then you'd have to worry. Okay, last example. Use a geometric series to write 7.181818181818. That's what the little line is, right? It's repeated 1/8 forever as a fraction. Now, I remember when I was a kid, I was taught the trick of if you have a decimal that stops, it goes over 100. If you have a decimal that repeats, it goes over some 9s, right? So the trick is this, 7.18 just, that stops at 1/8 is equal to 7 and 1/8 over 100. 7.18 repeating is very, very similar, but you change the 100 to a 99. If it's just a single decimal, right, then it would just be over 9. If it were 3 decimals that were repeating, it would be over 999. That was just a little method that elementary schools used to dish out back in my day, in the Stone Ages, right? Just to keep that in mind. But where does that technique come from? Okay, and that's what we're going to talk about right here. One of the ways that you can show that that technique is true is using geometric series. There's also some algebra that you can throw out to show that it's true. But let's use a geometric series since we're on that. Okay, so this is what I do. I rewrite this number as a series. Okay, now I'm going to say that it's 7 plus. The 7 itself is not part of the series, and that's because the 7 is not part of that pattern. If this had been 1/8, then I could have included it in the pattern, but it's not. So it's going to be 7 plus, and then you'll see I'm just going to carry the 7 plus, and it's not going to be part of the geometric series, but it's technically part of the value. Okay, now I'm going to start the series. I have 1/8, that's tenths and then hundredths. So that's 18 hundredths. Plus, the next 18 is thousandths and then 10 thousandths, right? So that's 18 over 10,000. Plus, what do you think the next two are going to be? I have tenths, hundredths, thousandths, 10 thousandths, hundred thousandths, and millionths, right? So that would be 18 millionths. Hopefully you're seeing the pattern here. I gain 2 zeros on my denominator every time I go up a term for the next pairing of the 18. Okay, so there is a definite pattern to my series there. Let's write it another way. 7 plus, and then I've got 18 times 10 to the negative 2. That's what 100 is, 10 squared, right? 10 to the negative 2. And then right here, plus 18 times 10 to the negative 4. And then the next one will be 18 times 10 to the negative 6. With me? Okay. So then, hopefully what you're seeing is that I can actually rewrite this in terms of the powers of these guys. Okay, so equals 7 plus, I have 18 times 10 to the negative 2, and now I'm going to use parentheses because this is an object that you're going to see repeated, plus 18 times 10 to the negative 2 squared. Negative 2 times 2, remember if you have a power to a power you multiply. So that gives me the negative 4 there. Plus 18 times 10 to the negative 2 cubed. Right? Whoops, I forgot my ... on that one. Do you see how this is forming into a geometric series? I have this one object that is continuing to grow in power, in exponent. So I could actually rewrite this as 7 plus the summation n equals 1 to infinity. Notice I had to go with 1 because this first one is to the 1 power here, right? Okay. And then it's 18 times 10 to the negative 2 to the n power. Because 10 to the negative 2 is the thing that I keep using as my thing here. All right. Well, now it's a geometric series plus some number 7, right? This is a geometric series. 10 to the negative 2 is just 1 over 100, which is definitely less than 1. 10 to the negative 2 is 1 over 100, which is less than size than 1. Absolutely, pun intended. Therefore, we can tell that this does converge. Obviously, we created it from a number, right? It better converge back to that same number. However, the fact that it converges in a geometric series is going to allow me to use my fraction setup to simplify it, and then I'll be able to have it in fraction form. Okay, so next, I've got that this is 7 plus. What is this going to converge to? I have to have my a over 1 minus r. So 1 minus r, I'm going to use 1 over 100 for the r. And my a is the first term of the series. Now remember, the 7 is not the first term. The first term of the series was the 18 over 100. So that's what I'm going to use, 18 over 100. And that's the same thing as this one. It's easier to write like this. But look at what happens. If I do my little technique where I multiply by that common denominator, I multiply everything by 100 here. That's going to be 7 plus 18 over 100 minus 1. And you'll notice that's where that technique I talked about earlier comes from. I'm going to get 18 over 99 there. So I have 7 plus 18 over 99. And in most cases, you could stop there, right? I'll have 7 and 18 99ths. But I can actually reduce 18 over 99. We'll have 7 and 2/11. It's a mixed number. So of course, if you want to take it to the letter of being literal, if you want to write this as completely as a fraction, I can then convert this into an improper fraction. 7 times 11 is 77 plus the 2, so I have 79/11 for that one. And then definitely double check yourself, right? In the calculator, 79 divided by 11 is 7.1818181818. Okay? So using geometric series, I can actually rewrite a repeating decimal as a fraction. So I hope that this lecture has helped you see these first two special kind of infinite series that we run into. Stay tuned for even more methods that we'll be using to test infinite series for convergence.